this part, we want to see how to get the force on a segment of wire. So this wire is just a straight segment of wire, small segment of length L, and the current in the wire is to the right, of course, as usual. Remember, the current doesn't have a direction, it's J that has a direction. So this arrow is the direction of J, which means the electric field is to the right. So the charges actually are moving, the free charges in the wire are moving to the left, with the velocity v to the left, opposite the electric field. So first, what's the direction of the force on this charge in the straight segment of wire? So the force is QV cross B. So V is to the left, and B is into the page. This wire exists in a region where there's a magnetic field into the page, denoted by these crosses. So if you get V cross B is downwards. But when you multiply by Q, because this is a negative charge, then the force is actually upwards. So the force on this segment of wire is upwards. Now, what about the magnitude? So we know the force on each charge is QV cross B. How would you get the force on the whole segment of the wire? So to get the force on the segment of the whole segment of the wire, you multiply the force on one charge by the number of charges. How can you write the number of charges in terms of variables you've taken before? We can write it as the number of charges per unit volume times the volume. And the number of charges per unit volume was small n, and the volume is just A, the area, times the length, so it's A times L. So you can multiply things out, and we get this result, that the force on the segment is QV cross B times NAL, where A is the area, small n is the number of charges per unit volume. Now, this is okay, but we want to try to rearrange the terms and write this in an easier way in terms of the current. So how do you think we can rearrange these terms in order to get to the stage where we can write it in terms of the current? Well, if you notice, by rearranging the terms, you have NQV times A. When you multiply these things by each other, what is the magnitude of these quantities when they're multiplied by each other? Remember, NQV, that's J, and J times the area. What's the magnitude of J times the area? It's just the current. Okay, and what's the direction of this quantity? It's the direction of J. And J is in the direction of the electric field, and the electric field is in the direction of the current, the so-called direction of the current that they put when they put on drawings, they put an arrow for the current. That's the direction of the electric field, the direction of J. So basically what we can do is we can replace all these by the magnitude, which is the current, I, and then the vector nature of these green variables, we can put it onto L. We can elevate L from being just a number, in this case, it's just a length. We can make L a vector. The direction of L vector will be taken from the direction of these quantities. And the magnitude of these quantities, we can just put the current I. So the direction of all this is the direction and the direction of the current. We can then replace all those variables by the magnitude of them gives you I, and then the direction of all those quantities, we can put it onto L. So now L becomes a vector. This is the way it's done typically in a textbook. So try to look at it a bit carefully and make sure you understand it well. So the force on this segment, I can write it in terms of the current, I, times an L vector. The L vector has a magnitude, the length, but the direction is in the direction of the current, which is the direction of J, which is the direction of the electric field. And then you take the cross product with the magnetic field. This formula will be much easier to use.